My name is Ayumu Yamatani. I'm here today to present a paper titled Secure and Timely GPU Execution in Cyber-Physical Systems, written by Jin Wen-Wan, Yuji Wan, and Nin Sham, Washington University in St. Louis, presented at the CS63 November 2023, Copenhagen, Denmark. GPUs, as graphics processing units, play an increasingly important role in real-time cyber-physical systems as more and more AI components are integrated into real-time safety-critical applications. Existing solutions for GPU Trusted Execution Environments (TEE) mostly focus on the assurance of confidentiality and integrity, but not availability. While existing solutions with availability guarantees focus only on CPU computing, it's essential for availability assurance solutions to support accelerators such as GPU. The authors introduced AVA GPU, a TEE designed to provide real-time availability guarantees for CPU tasks involving GPU execution on CPS in the presence of untrusted OS. To achieve this objective, AVA GPU addresses three technical challenges unique to GPU and beyond existing solutions. First, to prevent malicious resource contention due to separate scheduling of CPU and GPU tasks, they propose a CPU-GPU co-scheduling framework that couples the priority of CPU and GPU tasks. Second, they propose software-based secure preemption on GPU tasks to bound the degree of priority inversion on GPU. Third, they propose a new split design of GPU driver with minimized trusted computing base to achieve secure and efficient GPU management for CPS. A prototype of AVA GPU was implemented on the Jetson Edge X Orion platform, and the performance overhead is evaluated on Rodonia GPU on the SpecRate 2017 CPU benchmark suite. The real-time performance of AVA GPU is evaluated on both synthetic real-time GPU tasks and real-world applications. AVA GPU is designed to protect against privileged attackers capable of executing arbitrary code and reading-writing any memory in the REE on CPS platforms where GPU is shared between TEE and REE. It's important to clarify that AVA GPU focuses on computational availability guarantee of GPU tasks and is complementary to existing work that provides system availability guarantee with only CPU as a computational unit. Concretely, there are 6 unique attack vectors or threat models. From the perspective of GPU task execution, 1. Attackers can modify the GPU code and data stored in host buffers. 2. Attackers can manipulate the DMA controller to prevent GPU data transfer from completing correctly and promptly. 3. Attackers can manipulate CPU task and GPU task scheduling, which includes blocking GPU task command commits or submitting multiple GPU tasks to compete for shared resources such as cache or computation units on the GPU. In terms of GPU management, 4. Attackers may either deny access or maliciously configure the GPU, such as modifying the GPU frequency. 5. Attackers can manipulate GPU memory address translation by modifying the GPU page table entry and page table directory that refers to the table pointing to page tables for more granular address translation. 6. Attackers can exploit vulnerabilities of untrusted GPU tasks to arbitrarily read, write, and execute in their memory space. For each threat model, a security goal is defined to ensure that secure CPU and GPU tasks can complete correctly and timely. System goals are 1. Integrity of GPU task code and data. If a GPU task code and data integrity are not protected, it yields incorrect results. Thus, the first goal is to protect GPU task data and code integrity. 2. Secure GPU task input and output. GPUs use DMA to move data to the GPU buffer. Attackers could corrupt memory content of secure GPU tasks with malicious DMA transactions or delay them with lengthy data transfer. Therefore, other GPU should prevent malicious DMA write and preempting GPU data transfer operations. 3. Availability of GPU computation resources. Without access to proper configured GPU hardware, a GPU task cannot execute. Therefore, other GPU needs to ensure that secure tasks have access to correctly configured GPU computation resources. 4. Real-time protection for secure GPU tasks. Some CPS tasks requiring GPU computation are inherently real-time in nature. Latency computation results could lead to accidents. Thus, all secure real-time tasks utilizing GPU should have timely completions. 5. Isolation of GPU resources. A privileged attacker can maliciously manipulate GPU resource management, including GPU memory translation and command submission, to tamper with secure GPU tasks. Thus, other GPU must ensure the isolation of GPU resource management for secure and non-secure GPU tasks. 6. Maintaining a minimized TCB. Large TCB may introduce potential vulnerabilities. Therefore, other GPU aims to guarantee GPU availability while maintaining a minimal TCB. An overview of other GPU is shown in Figure 1. There are three key components corresponding to the challenges introduced in the previous slide. First, a secure CPU-GPU co-scheduling framework couples priority of CPU and GPU tasks, making GPU scheduler recognize GPU tasks' priority to guarantee their enough computation resources timely. Second, a software instrumentation-based secure and fine-grained GPU task preemption mechanism allows the GPU scheduler to reliably and effectively preempt GPU tasks, thereby effectively mitigating priority inversion. Third, a trusted GPU setup and management mechanism isolates secure tasks and essential GPU management functions from untrusted software to guarantee trusted GPU hardware configuration, dynamic resource management, and GPU task execution environment. Let me go through a few more details one by one. CPU-GPU co-scheduling infrastructure. The goal of the real-time CPU-GPU co-scheduler is to couple the priority for both CPU and GPU tasks, ensuring timely GPU-enabled task completion. But directly adopting the paradigm for CPU-GPU co-scheduling poses two new challenges. First, GPU lacks the individual word abstraction provided by ARM Trustzone, unlike the processor counterpart. This necessitates a flattened design on the scheduler. Second, the new co-scheduler has to ensure coherency of priority between hierarchical CPU scheduling and the flattened GPU scheduler. To tackle this challenge, they proposed to decouple the scheduler infrastructure of CPU scheduling and GPU scheduling while maintaining coherency on priority inheritance. The high-level design is shown in Figure 2, where the CPU scheduler is adopting the hierarchical scheduling while the GPU scheduler is flattened. To maintain coherency between the two, GPU execution strictly follows the word switching, where the accelerators prioritize on GPU tasks from the secure world when the processor is in secure state, and vice versa. Furthermore, within a single secure domain, GPU tasks inherit the priorities of the CPU tasks that are associating with. Secure GPU task preemption. Preemption is one of the important features in real-time systems, and there are two key design components to enable secure GPU task preemption. The first is task suspension and resumption, or task transformation. Other GPUs supports GPU task suspension by instrumenting the GPU task, enabling it to self-terminate at specified locations after execution context saving. This consists of two stages. First, other GPU prevents the GPU hardware scheduler from queuing task threads. Each GPU thread always processes one input unit. However, GPUs allow applications to submit tasks requiring more threads than the GPU's total core count. Consequently, excess threads execution are queued in hardware and scheduled by the GPU hardware scheduler. Second, other GPU proposes an event-based GPU task preemption approach utilizing customized compiler to instrument the GPU task. The instrumentation allows GPU tasks to self-monitor software preemption signals updated by trusted GPU scheduler. The second key design component is instrumentation modification and bypassing defense. Other GPU verifies the signature of instrumented non-secure GPU task hash prior to loading with the aim of identifying any instrumentation modification from REE. Other GPU detects progress delay by verifying whether the expected amount of computation is finished in a fixed amount of time. When control flow of secure GPU task reaches a delay checkpoint, the value of corresponding delay checkpoint pass value will be set. To verify the progress between two checkpoints at runtime, other GPU triggers the secure timer after a period from the previous delay checkpoint, checking whether the next checkpoint pass value variable is updated. If the next expected delay checkpoint pass variable value is not set, malicious GPU task contains shared resources. The preemption instrumentation is bypassed. As shown in Figure 4, the system is expected to pass through checkpoint 2 at time point T2. If checkpoint 2 is not passed at T2, an attack is occurring. As shown in Figure 5, the time slack between real-time task execution time and the deadline is limited. Detecting progress delay at the end of task execution may lead the task to miss its deadline. Furthermore, real-time systems often maintain a system utilization upper bound to make sure the system is schedulable, making other GPU has less time to eliminate progress delay. To solve this problem, other GPU inserts multiple delay checkpoints in a secure GPU task. In this way, the longest delay time of a GPU task will be the duration between two checkpoints. However, inserting more checkpoints will introduce more runtime overhead. With all these system constraints considered, other GPU generates the progress delay checkpoint strategy, given a user-provided real-time system utilization upper bound. The generated strategy guarantees that real-time tasks can complete in time after detecting GPU progress delay under the system utilization upper bound while maintaining a minimized runtime overhead. Trusted GPU setup and management. The GPU driver manages GPU, such as initializing GPU, managing power and memory, etc. Secure GPU tasks need trusted driver to have availability guarantee. However, directly migrating the GPU driver into the TEE significantly increases the TCB. Recent studies have replayed pre-recorded MMIO read-write sequences and values to operate I/O devices or accelerators, offering a trusted driver without substantially increasing the TCB. However, they cannot be directly applied to guarantee GPU availability. Shown in Figure 6a, it ensures confidentiality and integrity by isolating the trusted GPU replayer from the untrusted GPU stack. However, this approach doesn't prevent attacks from operating the GPU in the REE, leaving CPU availability unprotected. Similarly, as shown in Figure 6b, it protects availability of I/O devices using the global replayer in TEE, followed by an I/O reference monitor to verify the validity of all MMIO operations. However, existing design does not have dynamic memory management needed by GPU, including runtime allocated memory addresses and ring buffer pointer positions. Thus, as shown in Figure 6c, Alpha GPU offers secure dynamic resource management prior to the replayer, providing the runtime determined resource metadata for the replayer. Then, as shown in Figure 7, to prevent a trusted GPU driver while minimizing TCB, Alpha GPU provides a minimalist dynamic resource management of the GPU driver in the TEE. Dynamic memory management and GPU task commitment requests in the REE driver are trapped and verified in TEE before GPU task execution. Once resource management is completed in TEE, the GPU replayer operates GPU with the result metadata from resource management and recorded I/O transaction message. The GPU driver manages GPU memory to provide isolation among GPU tasks. To support trusted GPU memory management for secure GPU tasks, Alpha GPU manages GPU memory in TEE, but it introduces significant runtime overhead due to the context switch between the REE and TEE. To tackle this challenge, they built on top of the observation that most of the page table operations are read-only. Alpha GPU therefore only traps the security-sensitive write operations onto TEE. The GPU runtime library generates GPU commands that are submitted to the command buffer, and Alpha GPU synchronizes the GPU command buffer in the REE with the one in the TEE, from which the GPU fetches command. Code and data integrity of secure tasks should be protected from untrusted OS as they assure correct GPU task execution. Alpha GPU employs a DMA reference monitor in TEE to validate DMA memory access in GPU commands before GPU task execution. Specifically, the DMA reference monitor validates the source and destination addresses of DMA transfer commands from non-secure GPU tasks do not fall in the memory address space of secure GPU tasks before these commands are pushed into the command queue. The authors evaluated Alpha GPU using the prototype with the aim to answer 4 research questions. To address the first question, they conducted defense case studies to examine Alpha GPU's impact on 2 availability checks, which are malicious GPU frequency reduction and preemption bypassing attacks. To the second question, they measured Alpha GPU's system overhead on the Rodinia benchmark suite. To the third, they measured Alpha GPU's runtime overhead on Speculate 2017 benchmark, and to the fourth, they evaluated the real-time performance of the systematic real-time tasks and 3 real-world GPU tasks, as well as CPU hierarchical scheduling computation cost on micro benchmark. To demonstrate Ava GPU's effectiveness in defending against availability attacks, they conducted 2 case studies on the prototype platform using Ava GPU to defend against GPU working frequency reduction and preemption bypassing attacks. In a GPU working frequency reduction attack, an attacker with kernel privileges delays GPU task execution by reducing the GPU's working frequency. To delay the victim tasks as much as possible, the attacker lowers the GPU frequency from its highest setting, 1.3 GHz, to the lowest, 150 MHz, during the execution of the GPU task, causing CPU tasks to miss deadlines. In this case study, they selected open source applications commonly used on commercial drones, object detection using DetectNet, image classification with ImageNet, and image compression. These envisioned CPS applications operate autonomously under complex environments. As such, they often require powerful platforms with GPUs to support timely execution of object recognition, object classifications, or other complex algorithms. Each application has a 50 millisecond deadline corresponding to 20 FPS camera operation on a drone camera. Secure applications, which are object detection and image classification, operate in secure world, while the non-secure application, which is image compression, operates in normal world. The upper bound of the system utilization is 69%, aligned with the RM scheduling algorithm in their prototype. As indicated in Table 2, the average execution time for the 3 applications increases under a GPU working frequency reduction attack, resulting in a 85% deadline miss rate. However, with other GPU deployed, tasks meet deadlines even under this attack, with 7.52% increase in system utilization. This is because the GPU configuration mediator denies requests to reduce GPU execution frequency during secure task execution. In the case study of preemption bypassing attack defense, they evaluated the effectiveness of defending against preemption bypassing attacks on AutoWare, a widely used open-source autonomous driving software that requires high-end platform. Within AutoWare, perception tasks are crucial for detecting, recognizing, and tracking objects, with 3 object detection and tracking utilizing the GPU for accelerated processing. The correctness and availability of 3D object detection and tracking are the prerequisites of subsequent functions such as planning and controlling. And therefore, they protected it with Ava GPU in secure world. Other tasks such as sensor simulation run in normal world. The mission and map they used in simulation is sample Rosberg in AutoWare. They have profiled execution time of each task, setting the deadline equal to the period, which corresponds to the time interval between 2 consecutive task executions. They simulated the attack by exploiting the buffer overflow vulnerability in 5 synthetic non-secure GPU tasks that run a arithmetic computation loop to bypass the preemption, containing computation resources with victim GPU tasks. The buffer overflow vulnerability in untrusted GPU tasks is introduced at the end of the loop to override the loop condition, making loop execute without stopping. To show the effectiveness of defense mechanism, they measure the execution time of 3D object detection and tracking under 3 system deployment scenarios, as illustrated in Table 3. Under a preemption bypassing attack, the average GPU task execution delay is 6.99 times longer than the execution without an attack, exceeding the task deadline by 1.36 times. The auto-aware loss object perception of surrounding objects can be observed in visualized panel, impacting the availability of the following functionalities. When our GPU is deployed, the task meets its deadline even under a preemption bypassing attack, but with a 17% average increase in runtime overhead. To evaluate our GPU's runtime overhead on GPU tasks under different workload distributions, they measured the execution times of applications in linear benchmark suite on systems with and without our GPU. The maximum runtime overhead of each application when they lie in normal world and secure world is shown in Figure 8. The highest runtime overhead is 17.12% for k-means in normal world and 18.49% in secure world. The runtime overhead for each component in our GPU in normal world and secure world are presented in Table 4 and Table 5. Preemption checking and context switching exhibit the highest average runtime overhead among all components. This overhead is mainly due to checking variables shared between the CPU and GPU and restoring the execution context. The data transfer overhead primarily arises from extra DMA configurations due to transaction splitting, which increases in proportion to the size of the data. The code verification overhead, on the other hand, is solely caused by validating the GPU task code integrity in normal world, and it increases with the size of the code. The scheduler's runtime overhead is introduced by CPU-GPU co-scheduling. It fluctuates depending on various real-time task parameters throughout the system. The overhead incurred by memory management and command buffer management is primarily attributable to page table and command ring queue operations. The memory management overhead grows in proportion to the size of both the code and data of GPU tasks. This overhead also comprises the runtime overhead incurred by PTE checking in memory management mediator for non-secure GPU tasks. The configuration mediator overhead occurs due to the verification of the validity of GPU operation requests made from the normal world. Preemption bypassing attack detection runtime overhead is only introduced in secure tasks, mainly caused by checking the progress variables which are shared between CPU and GPU. The GPU context switching overhead is introduced by saving restoring registers on GPU task preemption and resuming. When comparing Table 4 and Table 5, the overall runtime overhead of GPU tasks in both the normal and secure worlds is similar due to a combination of factors. The highest average runtime overhead is mainly introduced by checking variables shared between the CPU and GPU and saving the list and restoring the execution context on GPU task preemption and resuming. Figure 9 illustrates the maximum memory overhead of each application when they run in normal world and secure world under different system utilizations. The memory overhead is mainly introduced by context saving when a GPU task is suspended. Among all applications in the benchmark, two bioinformatics processing programs, namely HERE and LUC, have the highest memory overhead, 37.98% and 31.10% in secure world, and 38.21%, 29.93% in normal world. These programs require a large number of registers for efficient computation, which are saved during context switching, thus leading to significant memory overhead. However, the memory overhead introduced by context saving is less than 10 MB, which is less than 0.04% of the total memory on their platform. To evaluate Java GPU's runtime overhead on CPU tasks, they measured the execution time of programs in Speculate 2017 benchmark running in normal and secure world on the system with and without Java GPU. As shown in Figure 10, the maximum, minimum, and average runtime overhead of Java GPU on the benchmark in both worlds are 6.87%, 0.23%, and 2.25% respectively. The runtime overhead on CPU tasks is introduced by a Stage 2 memory translation mechanism that is used to enforce memory access control, preventing attackers from manipulating GPU in normal world without being trapped into secure world for verification. In its additional page table works, introducing runtime overhead for CPU tasks. Java GPU guarantees the correctness of dynamic GPU resource management, GPU task commitment, and GPU configuration by taking over these operations from normal world GPU driver, that is, relaying these operations from normal world GPU driver to secure world. However, these modifications are all located in the normal world GPU driver, therefore having no impact on CPU tasks without GPU execution involved. To evaluate the real-time performance of Java GPU, they evaluated the real-time task miss rate for both synthetic real-time tasks and varying system workloads and real-world CPS GPU applications, demonstrating Java GPU's feasibility for real-world use cases. Real-time performance. In a system without Java GPU, all tasks miss their deadlines due to attackers submitting numerous GPU tasks in brief periods contending for computational resources. However, with Java GPU protection, benign tasks only begin to miss deadlines when system utilization of benign tasks exceeds 69%, in line with the theoretical result. Prioritized tasks start missing deadlines at higher utilization levels, since they are scheduled first when computational resources are limited. The real-time performance of synthetic tasks shows that Java GPU can maintain reasonable real-time performance under malicious GPU resource contention. Table 6 shows the real-time performance of a system running 3 real-world applications. The highest average runtime overhead, 16.2%, occurs in image compression in a normal world. It includes 0.7% configuration mediator checking overhead. Nevertheless, all applications complete their tasks before the deadline, proving the feasibility of Java GPU for systems running real-world applications. CPU hierarchical scheduling computation cost. They instrumented Java GPU hierarchical scheduler and normal world OS scheduler in Linux to record the scheduling event count and the total overhead over the execution of the same set of synthetic real-time tasks used in the real-time performance measurement. The total execution time of the task set is 15.79 seconds. Table 7 shows the computation cost of hierarchical scheduler when the system is schedulable. The normal world scheduler, which is a Linux scheduler, has significantly higher execution time compared to secure world scheduler and world scheduler because of complex data structure and process operations in Linux scheduler. Furthermore, the maximum scheduling events in normal world scheduler under different workloads is also higher than world scheduler and secure world scheduler. This is because Linux scheduler is jitter-based. Scheduler works at every fixed interval, while world scheduler and secure scheduler is event-driven, walk in only when a new scheduling event arises, such as the arrival of a new task. The maximum percentage of the execution time taken up by the hierarchical scheduling in our GPU across varying workload is 0.82%. Let me summarize. The authors introduced our GPU as a trusted execution environment, and it ensures real-time availability guarantees for safety-critical GPU tasks. Other GPUs proposes a secure real-time CPU-GPU co-scheduling framework, a secure and fine-grained GPU task preemption mechanism, and a new splitted GPU driver. A prototype on Jetson AGX Orion platform was evaluated with benchmarks, synthetic tasks, and real-world applications.